Well, we're on our way to proving that every Cauchy sequence is convergent. We already showed that every convergent sequence is Cauchy. So now we're trying to get to the point, which we will soon, that that converse statement is true. And to do that, we need to define what an accumulation point is. Let's let S be any non-empty set of the real line, or the real numbers. The number lowercase a in the real numbers is an accumulation point of the set S if every neighborhood of A contains infinitely many points of the set S. So let's look at some examples. Maybe I'll start this off with a question. If the number A is not an element of S, can it be an accumulation point of S? Well, you might suspect that the answer is yes, because you'll notice in the definition, S is a subset of the real numbers, non-empty. A is an element of the real line. It does not specifically say that it has to be a member of the set S. So the answer to this question is yes. Now let's give some examples. Let's just say that S is equal to the set of real numbers minus the number 10. So if I were to graph the set S, it would look like this. It's a shaded real line with everything shaded except for the number 10 where there's a hole in the graph. Well, if I take absolutely any neighborhood of the number 10, I'll take a little tiny epsilon neighborhood, say 9.9 to 10.1. That's a symmetric, I'll call that an epsilon neighborhood if epsilon were equal to 1/10. It's the number 10 plus or minus 0.1. This interval, so all the numbers between 9.9 and 10.1. This contains infinitely many numbers of this shaded region S. So there's a very simple example where the accumulation point is 10, and 10 is not in the set S. Let's take a look at, say S is this interval. Well, this interval, the number 0 is not in that interval. The number 1 is not in the interval. But in this case, A equals 0, I'll say, or A equal 1. Either one of those is an accumulation point of S. Can we say more about this? Yeah, we can. Every number in this interval is an accumulation point. Because from any point in this, if you choose one point and take an epsilon neighborhood around it of any size, you're going to get an infinite number of points of the set S. So I'll say that every point or every number in this set, every single one of them is an accumulation point of the set S. Let's do maybe two more simple examples. S is the set 1 over n. For all natural numbers n. So it contains the number 1, 1/2, 1/3, 1/4, 1/5, and so on. Well, we've seen this many times before. Is there an accumulation point for this set? Indeed there is. There's exactly one. 0 is the only accumulation point of S. And the way to think about that is 0 minus epsilon to 0 plus epsilon, which I should have just written that as negative epsilon to epsilon, for all positive numbers epsilon, this interval, which is centered at 0, contains infinitely many members of this set. And the last one we'll look at is, let's just say S is the set Z, the integers. Or I could have just said, let's consider the integers. Does the set of integers have an accumulation point? Well, no, it doesn't. It doesn't matter what integer you start with. I'll pick the number 15. That means the next one is 16, and the one before it is 14. Well, on the real line, I can find infinite number of intervals such that the only interval this contains in the set S, the integers, is 15. It contains one element only. So the set of integers contains no accumulation point.